Okay. Now, how do I know that the approach what I have taken that is more reliable or the single equation based models? Why I have compared it with Contd and Almendra? Because these days this is the most frequently referred model in our processing area. Okay. So, what I did, it is not an experimental data. I said, okay, let me do this calculation with some particles of quartz density particles, arbitrary numbers starting from different sizes, and let me calculate the velocity by the two methods. I have given this credit to Clift's book, it is Clift et al., it is Clift, Greb and Weber. For that relationship I have written only the code. Okay. Why should I say it is Majumdar's model? Okay. It is unfair. So, I have given the credit to Clift et al., and this is the Contd and Almendra. You see that up to a particle size, this is a finer size range, they agree with each other. So, if the both methods are correct, then I should get the similar value. But you see that when the size increases, there is a deviation between the predicted values of the two. Okay. So, there is disagreement. Now, which one I should accept? I will definitely say that it is based on the drag curve, because it has given the best approximation. But then I was looking for a good set of experimental data. Even if I ask someone that can you do an experiment for a settling velocity measurement for a particle into a. So, what do we normally do? We take a column like this, we dip a particle, but there is a lot of error in that, because there will be human error, there may be an initial velocity you are dropping it, and then when you are capturing it, because there will be, it is based on reflex, when you are measuring your eyes and all this. So, they are not reliable. I wanted to have a more sophisticated system which has measured this, and fortunately I came across one professor from Alaska Fairbanks, Professor Dan Walls, and for one of his consulting purposes, he had to set up this from a gold processing industry. They had given him a project that we cannot give you gold particles, but for a gold density particles, can you give me a data for different density variations from starting from a specific gravity of 2 to 19, different density, different sizes, but spherical particle will serve our purpose. But they will modify this your sphericity factor, okay, they will incorporate into that, but they want a measurement data. A professor said, Arun, I am not good at fluid mechanics, I have no knowledge about that, I was good at measuring something, and he is a mining engineer. Okay. That is the contribution of mining engineer also. So, he devised a system which I think is the best system I have come across in the literature for this type of measurement. What is the system? Let me first tell you. The same column is having, but what he did, he made the different density particles of spherical shape, and he doped each particle which you want to measure the settling velocity with some isotope. Okay. And then I know what is the density after giving that isotope, and then he has got two detectors, nucleonic detection system fixed at two different locations. So, that means the distance between this is fixed, okay, and the particle is being fed from here. So, and see that initial disturbances, to avoid that, he has put the first detection slate here, next one is that, and as I said that this distance is fixed, and for high density particle that will be travelling very fast. So, to reduce that velocity, what he did, he had upward rising velocity of water, just to reduce that. So, what I will add, the settling velocity, I know the velocity of this upward rising velocity, I will add to that measured settling velocity. So, that will be my settling velocity of my particle. So, that I get more time for my detection system to be triggered, because there will be a relaxation time also for that. So, to avoid that. Then what is happening? And then the flow rate and everything you are measuring, at what rate it is going. I know the cross sectional area of upward velocity of my water. So, I can calculate that, what is the velocity of this. Then when the particle is basically entering here, the detection system is sending a signal to my PC, that, and then there is a timer. I know that this is when it has basically reported here, and when it is just going out of this system, then again this another detection system is again detecting that particle. So, you know, if you have a timer, so you know how much of time it has taken, and you know the distance of that. So, I can easily calculate that velocity of that particle, and you add to that your upward velocity of your water. So, you get the settling velocity of that particle. Okay. So, I thought that very accurate, but still there will be error. I did not go for error analysis and all this, but he gave me a report of that, this is what confidential report, but I said that I will not mention about the company's name and all this, but I need to do it for my analysis purposes. Then what I did, this is the Danvers data comparison. Now I am comparing with measured data with these two different models, two different approaches, Cliff's method, iteration method, and Concha and Almendra's method. And what I have seen, that your measured data and predicted data from this two system, the Cliff's method gave me 11% error at 95% confidence interval, but as I said that it is not the weighted average data of the measured data, because I could not get hold of those detailed data. Probably he was having some limitations of giving me the entire data set. So, whatever data I got, so this data could be further refined, but this is also the problem even for measuring the settling velocity of a particle. It is not that simple. Okay. So, then I got 11% and 14%, not much difference is there, but still I would prefer that iteration method over this. And unfortunately, this size ranges what he has dealt with is a very fine size range, and we have seen that even synthetic data fine size range, not much deviation is there. If it is coarser particle, I am very sure this differences in this will go up. So, personally I recommend that if you think that your settling velocity information is very, very important for your designing purposes or process improvement purposes, please write a small code. This may be an assignment for you, that is, can you write a code with that MATLAB or whatever language you are comfortable with. That will be a good exercise for coding also. It will not take much time if you are comfortable with coding. Why don't you show me that you can calculate the settling velocity based on this correlations. Correlations are given, procedure is basically discussed. So, if any one of you or if all of you are interested in coding, why don't you write a code and show me before you leave this institute on 18th that this is how it is I am getting. And all of you can check that what is the number you are getting for a particular size and density and what others are getting, they must match if you are following the same procedure. Okay? That you can do it. So, once you have written a code, then you can forget because it is one time job, then you are not calculating again and again, you are just giving input variables. Now, so for this the free settling velocity, I mentioned, probably you have looked at that, initially I said it is free settling velocity, but I leave it to the end of this part to discuss what do I mean by free settling velocity. Free does not mean a single particle. It is basically the relative concentration of my particles and the fluid concentration. It is no other than our Einstein, who proposed, actually he also started his career in this line on movement of solids in waves, in sea waves and all this. And so that is where he has given the viscosity equation what Professor Chakraborty was yesterday telling, and then he said that it is very difficult domain for me to continue this research, probably it will take 100 more years to come out with some plausible solutions. So, let me quit and get into the basic physics. So, his initial career started with this field. Okay. So, Einstein, according to Einstein, that you can apply free settling velocity model if your total solid concentration is less than 5% by volume, but now that is being argued in literature, and I also personally believe that 5% is a little bit higher side by volume. So, people advocate these days that less than 2%, less than or equal to 2% by volume, you can safely use free settling. Now, what I will be using, why I am saying, I will again reiterate this point when we talk about the other topic like hindered settling. Okay. So, the conclusions for this free settling part, I will say that Clift et al.'s correlation gives the best approximation of the drag curve so far, and the iterative technique developed is quite accurate to predict particles' free settling velocities, as it is based on the best available correlations. And single equations proposed in the literature may not be accurate always. Okay. So, be careful when you are using a single equation, you try to identify what is the core CD and RE correlation that is being used for development of that model, and you look at the standard drag curve, plot it into an Excel, then only you accept that single equation, otherwise please do not accept that single equation, may be written in any journal. Okay. It is my advice. Now, what happens, this problem, this part probably Professor Eric will like to deal with at much greater depth, and this is called the unsteady accelerating particle motion, because initial equation I have set dV by dt is equal to 0, but many times I may not be able to give the sufficient time for the particles to reach terminal settling velocity. So, I want to separate them, still they are accelerating, but we hardly use this. In mineral processing, we hardly have any separator where we do not give sufficient time to reach the terminal settling velocity, but there are many systems where you may not be able to give the particle to reach its terminal settling velocity. So, you have to deal with the accelerating motion, that becomes complicated. So, what happens in an unsteady accelerating particle motion, I am not aware of the latest development, it is 5-6 years old information. You may get the latest information from Professor Eric on this, because now when the particle is accelerating, you have to account for some additional forces, not only these three forces, that is your gravity, buoyancy and drag. So, what are these three forces, additional forces? What happens if my particle is hydrophilic, then what will happen? Immediately when it gets dipped into the water, there will be a small layer of water on the surface of my particle. So, that depends on whether my particle is hydrophobic or hydrophilic. So, then it is moving with that envelope of water also. So, you have basically changed the mass of that particle. Are you getting there what I am trying to say? So, that is called the added mass term, but how do I know how much is added or not? It is a very complicated area, that is also dependent on the surface property of my particle. It is very difficult to do that. And then there is a Bassett history term which corrects the drag for the transient conditions, because what will happen? Now, initially the particle when started, it has got mass of x, so my drag is different. Now, when I am having x plus delta x, so drag is different. So, that is the transient conditions, unless and until it reaches the steady state condition, it will still be having, say the coding will not be having, I am talking about your very small time domain, as a millisecond region, maybe fraction of millisecond region, but still there is a transient region, that is how the mass is being added to the surface of that particle. Okay. This is what I said, that This is where we differ from the basic fluid mechanics people doing research in this area, and we the mineral processing people deal with that. I say that okay, that may be a fascinating, interesting research area for that, but I am not dealing with 1 or 2 particles. My volume of particles is much more. So, I just need a model that which will best suited to my process, that is it. You keep on doing the research, I will borrow that knowledge from that and I will use them. Okay. So, even for this, for a very low values of Re, the creeping flow, you know what is creeping flow? As a your viscous flow, actually just a streamline flow. Very low values of Reynolds number, I have got an equation for that, and this equation is this, that is rho p, that is the particle density, plus that rho f by 2, that is how much of the fluid will get into that is rho f by 2, and all these terms are there. I do not want to spend much more time, and this is the added mass term, and this is the fluid drag now, this is the Stokes drag, and this is the history integral. I do not know how to solve it, but or personally I am not interested to find a solution for that. Maybe the fluid mechanics people, hardcore fluid mechanics people may like to talk on that. That is why initially this lecture was supposed to be given by Professor Eric, the movement of solids and fluids, because when a fluid mechanics person is eager to give a talk, who am I to give a talk? But when there is some change in his schedule, so I said, I wrote him that without this I cannot teach further. So please allow me to talk whatever little knowledge I have. He said, Arun, you go ahead, but I will have again, if I reach there, I will have a session that to revisiting this. That means he knows that a mining engineer, mineral processing engineer cannot teach it, and I am very sure he will try to more emphasis on these terms because they require it. Because when you are dealing with, say suppose you have to understand the area of research, that is what I am saying. His area of research is how the bacteria they move in a fluid medium. Okay. So, and it has got an elastic and type of motion, you know, they move like this. So, it is very difficult to, and so that is one of his article published in Nature. So, that type, but here we are not dealing with the small bacteria, so we are dealing with huge large tonnages of materials. Okay. So, rather for mineral processing purposes, I do not think that right now to solve the problems, we do not need to go up to this level that what will be that and all this, you know, in an accelerating motion. We can safely discard that portion, we can start with your terminal settling velocity problem. But if someone of you, if you want to pursue research in suppose your blood flow and all this, you know, you may require all this. I am not saying this is not required, it is required. But for mineral processing application, again and again I am saying we may not require, and that is where I say that where do I compromise, how much of fluid mechanics I should go ahead and where do I leave that field, and I will bring back to my main focus. Okay. So, this is the complicated equation and it is very difficult to solve, but what I did, that is, yes, I know how to use them. I just for my curiosity I wanted to look at, that is, if I do not use any of these terms, then what will happen to the predictions. And you see that what happened if I use a full solution, and you have to make it dimensionless and all this, dimensionless velocity, dimensionless time, it is not that easy straightforward that you can use it, that equation then. So, I did this exercise, and if I am using a full solution, that is a full equation, I am getting a correlation of your dimensionless time versus velocity in this. Now, I said that okay, if I neglect history term, that means what is the sensitivity of each term on my prediction. It is one way of doing sensitivity analysis, that if I neglect the history term, what will happen? This will over predict like this, and if I neglect both history and added mass, then it will over predict. So, that means if I want to use, if I want to know the accelerating velocity, there is no other option, you have to use the full solution. But still nobody, I have not come across, I should not say nobody has done it, I have not come across a literature which validates this with measurement. How you are going to measure it? The accelerating velocity. Even for terminal velocity you need all sorts of sophistication, like doping with isotope, and you need nuclear density gauges and detector system. For accelerating velocity in a millisecond or fraction of a millisecond interval, how we are going to measure? If you have bright ideas to measure even settling velocities, probably again you can publish good articles. Maybe the consulting companies, they will borrow, the design companies will borrow those things from you, but these are extremely difficult things. The measurement, I say that for this type of system, the main problem is with the measurement, okay, accuracy, with degree of accuracy, not precision, accuracy. Now, I will come to non-spherical particle system. So, that is about the spherical particle system, pre-settling conditions. Now, what will happen if I have a non-spherical geometry? That is what mostly we encounter in this type of industry and in nature, natural mineral, when you try to handle, you hardly get spherical particles. Okay. So, non-spherical particles I have already discussed in my particle characterization lecture, that is how do I measure the size, and ambiguities are there. So, I do not want to repeat that. I will straight away come, that is commonly used measures for this, that size we say equal volume sphere diameter or Stokes diameter, they will say, but Stokes diameter means it is only Stokes region. That time I did not say, people say Stokes diameter, but Stokes diameter you can only apply when it follows Stokes law. That is, by using Stokes correlation, you have calculated what is the basically the size of the particle, equivalent size of the particle. So, rather we can use the equal volume sphere diameter, a general relationship like this, and shape we have already discussed, that is the sphericity, that is surface area of equal volume sphere divided by surface area of particle. Here I will bring the Professor Chhabra's one of the papers, okay, where one of his PhD students, he has compared all these models of non-spherical particles models, and it is published in Powder Technology, and I will show you the case, okay, slowly. So, this we have already discussed, that if I L by D changes, what sphericity you take. Some popular correlations, and look at the name of the people who are from chemical engineering, they are all familiar probably, Harder and Levenspiel again, okay. For non-spherical particles, these are the equations they are given. It is all basically empirical relations, ugly empirical relationship. So, empirical, why I am hammering on this point? Because if you are using this, you must look at the paper, that what type of system they have used, what type of particles they have used. Now, first before you use that, you must confirm that the particles fluid system what you are going to use for, to use that model, that has got identical similarity with that system what is used. Otherwise, what will happen? Look at these empirical parameters, like your say A is equal to 0.81. For your sample, for your material, is it also correct that I should use 0.181? So, what I have to do? I have to check that whether his system, based on which he has generated the data, my system is also identical to that. Otherwise, you cannot apply the empirical models, or be prepared to introduce large errors into that prediction. But I must know then it should be followed by some measurements then, how much is the error, okay. Otherwise, just randomly if you use a model, no, I am not going to accept that, and you should not also. So, these are the models proposed by this great gentleman in 1989. Ganser, these are all famous models, okay. You see, these are all basically empirical. I am not going to discuss all this, you can look at their papers. Chen, these are all very famous models, very frequently referred into literature for non-spherical particles. And so, the question came, that is not my work, this is Professor Chhabra's work with his student, he published in 1999, that which one is the best? If I compare, another message I want to give here, that look at the data bank, that is sphericity varies from 0.09 to 1, that means large particle domain, shape domain, the data was taken. Reynolds number range 10 to the power minus 4 to 10 to the power 5, Hughes size range, it was covered. huge size range with huge your differences in the shapes. All this data were accumulated, that is the PhD of one of his students. Okay. So, and then what he did, that he wanted to, that is all measured data. He wanted to compare it with the predicted data by using these models. Hyder and Levenspiel mean error were 21.5, Ganser 16.3 and 23.5. Looking at the complexity of the system, the mean of around 20% is quite good. I would say it's quite good, because we all know that what are the complexity, orientation problem, so many ambiguities are there. If someone guarantees me that this has got 20% error, I will introduce that error into my model. I know that what will be the reliability of my system, and that is what the best model given. But this is the great message I want to pass on. Don't look at only the mean error. Please don't look at the mean value only. You look at the mean varies from where to where. What is the lowest value and what is the highest value of that error. That is a very, very important message, irrespective of which area you will be working. And you look at Hyder and Levenspiel, maximum error was 276%. When you are minimizing it, you are getting a mean, but you are having 276, 181, 153. Now, can you guarantee that for your data, it is not belonging to that group? How do we answer? So, that is the risk of using or choosing a model based on the mean value. Please do not do that, you must look at. So, the conclusion is, none of these models are reliable. It is your own judgment which one you will take, and better it should be supported by some experimental data. And then you see that which one is better predicting. If it is not predicting, you just develop your own correlation, if and if you think that this is very, very important parameter for your system, whatever it is, whether you are design engineer, process engineer, for what purposes. Okay. So, this is with the non-spherical particle system, that is the scenario. So, in a nutshell, not reliable model, no reliable model is available for non-spherical system. There are models, but you have to be very, very careful before selecting a model, that whether how much of error will be introduced into that, what are the systems they have used for that model development, whether my system is identical to that or not. This is very, this is the caution. Okay. Now, this is the hindered settling. What do I mean? This analogy I give because I think you can correlate. When I teach in my class also, I give that what is free settling and what is hindered settling. Okay. And I have also written spherical particles, so I am not going to deal with non-spherical particles because there are problems. Okay. The problem is not with me, problem is with the entire scientific community. Okay. So, hindered settling, this analogy I will give you, like let us say in a highway you are driving your car. The highway the limitation is 100 kilometers per hour. You see the road is smooth, and if you want to drive it at 100, is it necessary that you have to be alone in the entire highway? No, there should be less traffic, so that the probability of hitting another vehicle is less. It means you can maintain a certain distance most other vehicles, and the road is smooth, safe driving condition. So, you can easily drive at 100 kilometer per hour, that is your terminal setting velocity, that is the maximum velocity. And if you have a cruise control, you know what is cruise control, you can just press a button and you can withdraw your leg from the accelerator, it will go on at 100 kilometer per hour. There are many vehicles in India also, you are having cruise control. Okay. But the moment the traffic congestion starts, you will find that the moment you are very near to the main city, you will find that the traffic is basically the density is going up, and automatically you will find that you are slowing down the vehicle. From 100 you have brought it 80, 80 to 60. Now there is no direct contact with other vehicle, otherwise we will have an accident. But why you are reducing? Now the distance between another vehicle which is in front is getting reduced, and even the sides, there are so many vehicles are passing by. So you want to have proper control with your vehicle, because even 1 centimeter here and there may bring accident. Okay? Although you are not having direct contact with the vehicle. Then if the traffic congestion, so that means with the crowding of the traffic, automatically your velocity is going down, the speed of that going down, and a moment might occur that you do not have a free space to go ahead, you will become standstill. Although you are not hitting anyone, otherwise there will be an accident. I am trying to stress upon that. It is not necessary that you have to hit another particle, otherwise there will be accident. So what is the maximum limitation of your speed? That is 100 km per hour. So hindered means it is a hindrance by crowding. So your velocity will be reduced. Now for particle system also it happens. Now if my system, if I have very less particle, that is what I said Einstein proposed, say less than or equal to 5% by volume. Now people are saying 1% or 2% is rather more conservative, more safer assumptions. Okay, this is what I also personally do. Up to 2% now I am using the free settling velocity. That means I can drive my vehicle at 100 km per hour. That is what we have derived or calculated. So that velocity I can use. But in processing circuit, in mineral processing and coal processing, again and again I am saying that I have to process large tonnages of material per unit time. So our job is that to optimize the parameters so that we can process large quantity of material per unit time. So I will be preferring a crowding atmosphere than a free settling atmosphere, because free settling atmosphere is best for separation, probably may not be always true. I will show you an example later stage, but then the capacity of my equipment will be very less. So how far we can go, that is the main variable we study in any equipment. All people who are involved in this, that what is the pulp density or what is the percentage solids I can process. So my answer is that it depends on system. There is no generic rule, and you have to look at what is the settling velocity difference you are creating, and the more crowding means my particles will be having more resistance to flow because of another particle movement. So the viscosity of my fluid also may be changed because of more crowding effect. Okay. So these things, if I want to quantify, that is called the hindered settling velocity. How do I quantify? Okay. Now for that I have to know that what are the possible reasons for hindrance, and this is nothing but incorporating a correction factor to your free settling velocity. So hindered settling velocity is always less than the free settling velocity of my particle. You keep that example into your mind, traffic that only you can drive maximum at 100 km per hour. Now if I want to quantify them, I have to understand what are the reasons for hindrance. First thing is that a decrease in the available cross section for the upward flow of the fluid, which results in an increased fluid approach velocity. What does it mean? Now when the particle wants to go down, it will be displacing the fluid upwards, but when it is the fluid wants to go up, but it is hitting another particle. So what is happening? So you are creating a resistance to the upward flow of the liquid. So automatically your downward velocity of my particle will be reduced, because if it cannot displace that fluid, it cannot go down. So automatically, so that is what it is trying to say. Okay, that is your decrease in the available cross section, because if I have only 5, 6, 10 particles in this bottle, even the fluid upward fluid will have many routes to go up. but if I have 30% by volume, then it has to reduce its upward velocity to find a possible path. So, when the upward velocity of the fluid is reduced, downward velocity of my particle will be reduced. That means, my setting velocity will be reduced. Then an increase in the apparent viscosity of the pulp. Pulp means it is the mixture, it is the suspension. We use this term pulp, sometimes we call it slurry. Okay. So, there is some difference in that, but it just for this understanding purpose, it is the solid liquid mixture. Okay. So, what will happen? The apparent viscosity. So, that means resistance to the flow will be there, entire thing, because I am talking about upward velocity, but at the same time, if the particles are basically suspended, when my one particle trying to go down, it may hit another particle, and the particle density, that is a suspending fluid, what it will be displacing. So, you are not displacing only that water, you are also, you have to displace also the suspension. So, the viscosity of the resistance to flow will be more, there is nothing but the viscosity, but it depends on what type of particle you are feeding. If it is coarse particle, the viscosity may not be affected. So, for that I must have a viscosity model for non-Newtonian fluids. So, that is what the problem we face when we deal with clays, like your iron ore processing, we deal with clays, coal processing. The clays are very fine particles and they remain suspended. I introduce your viscosity problem into that. Then a decrease in the gravitational driving force due to a decrease in the difference in apparent specific gravity between the particles and the pulp. I said that it is an initial equation, it is the basically difference between your buoyancy is in the function of rho f, that is the rho fluid by rho particle. Now, the rho f is changed, rho f is increased. So, I have a problem now. So, that will be also reducing my parameter, because that component will go up. So, mg minus mg into rho f by rho p will go up. So, my difference will be less. So, my net velocity will be less. Okay. And increase in the wall hindrance, that is what I said at the beginning, that how big is the chamber. So, now in my road I have got only 2 lanes road, now I am having more traffic. So, the wall, that is your air what you are basically say displacing, and then your wall effect means other effects like another car is there that side. So, I have to be careful of that, and there are pedestrians this side. So, I have to be careful about that. So, I cannot drive it at a very high speed. So, I have to reduce the velocity, that is the for simple discussion's sake I call it wall effect. Okay. And also if my particles are closer to the wall, because some particles will be closer to the wall when I have more crowd. So, the my velocity of my water which is very near to the wall, that is also very less, the basic principle of fluid flow, because of viscous forces will be more dominant. So, when my velocity of upward velocity of my flow is getting basically having a resistance because of the wall, my downward velocity of my particle also will be less. So, I have to sum up all this, there are many other things also. So, you have to have a model for hindered setting velocity, and these models are nothing but to incorporate a correction factor to my free settling velocity. Okay. What is the most popular? Chemical engineers, they are all familiar with, I guess, Richardson and Zaki. Who is not familiar? The chemical engineer. Are you familiar? Chemical engineers? Not? Oh my God. So, okay, you are all second year probably, but you are in third year, you are not? You have not read their book, Richardson Colson? So, that same Richardson. So, this Richardson and Zaki model are the most popular model by the chemical engineers, but I won't recommend it for mineral processing engineers, because chemical engineering system mostly you deal with monodensity particulate systems. You do not have polydensity suspensions. Okay. So, polydense particle system, that means you do not have a density variation in most of the cases. You may have size variations, you may have same size more particles, like your say reactor designs and all this, that composition does not change, size does not change, density does not change, but you are having more particles to deal with per unit time. That system is different than our mineral processing or processing system, where I have got a variation of size, I have got a variation of density. So, it is called polydisperse and polydense suspensions in our case. Okay. So, anyway, but when I do not have any other better method, many times we use it, we are forced to use it, but be careful that it is not the ideal model. This model was not developed for to deal with polydisperse and polydense suspensions. Okay. So, what it is telling? Richardson and Zaki is VTH, H has come now with T, that is the to denote hindered. So, it is the hindered terminal settling velocity. That is terminal settling velocity, but in hindered conditions. Okay. That is equal to Vt, that is the terminal settling velocity, and this is the correction factor. So, no way in any case I have to calculate this Vt, that is the free setting velocity I have to calculate. So, for that the first part of this talk was based on that, that is which free setting model I will be using. Okay. Then what is C? C is the total volumetric concentration of my particle, and N is a constant which varies from 2.33 to 4.65. No N value was proposed. So, you have to determine the value of N for your system, even to use Richardson and Zaki. So, that means again and again I am saying that you have to have some kind of measurement. So, this is also part of particle characterization, or I would say to understand particle fluid characterization, and if you are dealing with this process related thing, I have to have a good backup with my experimentation system, because most of these correlations are empirical, I have to deal with that. So, this book Mod and Whitmore, this Richardson and Zaki, they have again developed this model for pharmaceutical industry purposes. They have given a different N value, which chemical engineers, they say that it is not always acceptable. So, then there is an article like Mod and Whitmore, these two gentlemen, they said no, I have done with many different systems and we have found that N varies from 2.33 to 4.65, but again for my system which value I will be using. So, again a little bit contribution has come from one mineral processing engineer based in Australia, is Hollenbat, and to help the mineral processing industry people, he did some systematic test and with measurements and all that. Then he proposed that I can use N is equal to, but I do not know how accurate it is, I cannot guarantee that whether it will be useful for any system, but when you do not have anything you can use it and you refer it, that is I am following that. Okay. So, 4.6 minus Re, and this is all correlation of Re, it does not give a value. So, I can easily incorporate that and I can calculate Re from my system and I can get a value of N. Okay. Are you getting there? Okay. So, limitation of this model, that is what at the beginning I said, that I will show you the most popular models and their limitations and which one I should use. That it is applicable only to uniform density and monodisperse suspensions. Like say suppose if I am trying to fluidize in a air medium the homeopathic nodules of equal size and density then probably I can use this, but not for coal or mineral particles. If I do not have any other option I will use it, but as I said I have to give reference. Okay. I have to be very careful, the error could come from there. Now again this Lee is again basically a student of Professor Concha. Again this model is being used extensively by the mineral processing engineers for designing purposes, for software purposes, and again I have got some limitation in accepting it 100%. Okay. I will explain that. So, this is nothing but it is an extension of initial Concha's and Almendra's model of hindered setting. What he did, for what he did, it may look again a congested one, but if you look at carefully it is not very difficult model, it is only an empirical relation. Okay. That is mu f is the viscosity of the fluid, there are two functions f1 and f2, again the C stands for the volumetric concentration. Here everywhere you have to use the volumetric concentration, because my viscosity and displacement they are all functions of volume. of the particles, the volume occupied by the particles, not by the mass of the particle. Okay. So, this is basically function of that, and what corrections he has incorporated, this Mr. Lee or say Dr. Lee, that instead of using rho f, that is the fluid density, he has suggested that you use the pulp density, that is the slurry density of that. Okay. Now, the problem comes, say suppose again I can give you a reference of Kim and Klima. These are very interesting, fascinating field of research and lot of industrial applications also. But the problem with this, first problem, now say suppose I have got a column like this, and then I have got water, and my particles are, I have dropped different particles, okay, different density and different sizes. As I suppose this is occupying 20% of volume. So, I will calculate that if I have this much of water, if I have 20% of this, what will be rho pulp? Fine, I can use all the values. But what will happen after delta T, because of the size and density changes, if I split it into different segments, I will already have a separation of these particles coming somewhere, bigger particles coming somewhere, and smaller particles remaining somewhere. Are you getting there? So, the pulp density here is different and here is different now. How do I predict which particle concentration will be where and how much? And this is called zone settling. Okay. So, these are basically on reactors and all this. If you are basically keen to design, I must solve this. Even for fluidizations and all this, you must take bed density, you take, but what is the particle, say nature of particles at different layers, must know that. So, in this case also it is required. So, I cannot arbitrarily use, but his purpose of doing that is to develop a model for dealing with hindered settling. Now, it is your job to find out first that how do I use it. So, it should be a function of your local particle concentration, but how do I know local particle concentration? It is a big challenge. That is, in my gravity concentration talk, I will show you that how did I solve this problem for another system, that, but you have to wait for that. When you come to that, talk about. But this has got huge challenge even for your summer vacations and all this. You can take it up as a project and can do the experiments. You can think of an experimental setup, and this is a very good rigorous mathematical analysis, computational domain you can go for. You can go for CFDs, DA, whatever it is, whatever you like these days, softwares and all this, but you have to bring realistic values, you have to validate it. And it has got huge application. Even say Dr. Subramaniam will agree that he is also working to some extent in that area, and you have to bring that type of your concentration gradients. Otherwise, that would be my starting model, but just after delta T time my concentration changes at different layers. So, I cannot give only one unique value of concentration, it should be changed with time, is not it. So, that is a big problem, that is a major, that is one problem of this, but that is from a user point of view, that is the problem remains with any model of such kind. That is not the problem of with the Lee, but the problem with the basically the user, how do I use it. But what limitation I will have in accepting this, that is when I looked at it, I said okay, it is only having the total solid concentration and you have corrected the rho pulp. I had got two limitation, one I still do not know what is the answer. My supervisor said, no Arun, we must not take rho pulp, you are not displacing the pulp, you are displacing only the local fluid. So, we should use the local fluid density only, there is no need to correct it. Okay. And again I said that his logics to understand is beyond my capability, and I was not doing research on this. But when you are referring a model, when you are using a model, you follow line by line of that what he is saying. So, that is one, and my major complaint, major limitation of this, what I think, that is what will happen. So, suppose this system, that is what one day I told about thickener. Now, the bigger and say suppose this is the highest mass particle, when it is trying to go down. So, it will have some rising water velocity because of displacement. Now, if this rising water velocity also will hinder the movement of these smaller particles, does it account for that? No, you are only taking the total concentration. So, that is called the counter flow factor. Because of my big brothers are trying to go faster, so your little brothers will have difficulties, they have to further slow down. So, where is that factor coming out? So, I need another correction factor to my hindered settling velocity when I have polydisperse and polydense suspensions. Are you getting there? So, when I have a density variation, when I have a size variation, so I must introduce that. So, when I was not convinced, I was looking for a better model, and I explained it to my supervisors, and my main supervisor Jeff Lyman, he said, Arun, what literature you have looked at? I said, all. Then he said, that is also another dimension of literature review. He said, I will looked at Russian literature, I will looked at German literature, I will looked at French literature. I said, I don't know. I said, then you cannot say that I have covered all the literature. Have you covered Chinese literature? Then he said politely, Arun, I have little bit knowledge in German, and I came across one article published in 1970s or somewhere, that has got this factor, I remember. Why don't you catch hold of that? I looked at it, and I told him, Jeff, I got a reference for the thesis, this was thesis in German. I said, go and get it. How do I get it? So, it is very simple, you speak to a librarian, you will get it. I went to the librarian of the JK Mercy. She said, okay, Arun, give me the reference and let me know the project number from where the money will be deducted. Project number I have given. You won't believe, within 7 days I got the photocopy of that thesis, German. That type of arrangement they have, you get. When I got the thesis, I am saying that if you are serious about your research, you have to do this. It is all written in German. Then I said, Jeff, what do I do? Get it translated, man. So who will translate it? I had my friend there, she was also doing PhD, she is a German, Yvonne, and I requested her, Yvonne, can you do it? Here actually when we approach to a friend, we think that we don't even think of the paying money. We think, okay, it's my right. She said, Arun, yes, I am ready to do it, but you have to pay for that. I said, okay, how much will you charge? I thought she will say that, okay, one dinner or something. I said, no, you have to pay me $40 per page. Yes. Nothing is free, that is professional, that is good, I appreciate. Then again I spoke to my bosses and they said, okay, book it from the project. But there is no point in getting the graphs translated, only for single lines you will charge, because that will also cover a page. So, graphs, let it be like that, you will understand, and if you have difficulty I will tell what is that written. Okay. I paid around $7,000 from my project to that girl to get it translated, only to get hold of a model, and that also I was not sure that whether it is good or bad or nothing, just to evaluate it. And that kind of sincerity, that kind of your openness, you have that. Okay. So, what is that model? It is called the Brouwer and Thiele's model. Bit complicated, don't try to understand it, but just keep it in your mind and keep this presentation. If any time as a designer, if you need to use a better model, you get hold of this model. That is what my purpose of telling it. And you see that, and I have used it extensively. Okay. So, it is basically, it is saying that is I is coming, that is for ith particle. Has introduced I, that is the hindered settling velocity, because I am not talking about the velocity of the entire assemblies. That in a hindered settling condition, polydisperse and polydense condition, I want to know the velocity of a particular particle class, that is the ith particle class. That is why the I has come. Again, T and H stands for terminal and hindered. And you see that there are two correction factors now. Now, I is again ith particle, C stands for counter flow factor, which takes into account of that. That is your big brothers disturbing the younger brothers. Okay. And Is is nothing but the normal correction factor, that is called the swarm velocity. That is the technical term used in this type of fluid mechanics literature, and it is nothing but what similar to that Richardson and Zaki's correction factor, that is called the swarm velocity. Now, these are the two formulas. How do I use them? That is, to use it, first what it is suggesting that you have to group them as per your the highest density with respect to density of other particles. That is, in your entire assemblies, what is the highest density particle you have and what is the coarsest particle size you have. Then relative to that, you have a ratio highest to lowest and different density sizes. So, you group them with different dp pi divided by dpn, that is the dpn is the largest particle, nth particle size, what is the largest particle size, what is the diameter of that, and then with that what is the ratio of this ith particle of your interest, what you want to know. And for this, that is the dimensionless density, you can term into respect to fluid, you have to bring that what is the dimensionless density for my ith particle. But I propose that, I thought that I will write an article, but I could not find time to do it. But I think the best way, again you have got two variations, dimensionless size and dimensionless density, but if I incorporate a Reynolds number, I can even group them amongst them. That is the size density I can correlate by categories. But as I said, when I am using someone's model, if I am giving credit to him, the discredit also goes to them if there is any. So, I am referring that and I have to follow in ditto. Okay. So, that is how by using this formula you can get this factor KIC. As I said, do not worry about that. If you someone is very much interested in knowing this, but first you have to convince that why you want to know this. They come to me, I will give you my Excel spreadsheet, I can spend hours on explaining that, I can help, but you have to first convince me that why do you need that. Okay. Then KIC you can find from this, and KIS, that swarm velocity, you can get from that. And applicable when C greater than 0.05, that is more than 5% by volume, that is what the Einstein's reference they have given, but I would say it should be more than 2% if it is there, can use it. Okay. And n has to be greater than 1, that is number of particles, say nature of the particles should be more than 1 classes. Okay. That is for, and if you put the values to that, you can get back to the, you can check it, I have not checked it, that whether I can get back to the value of model of Richardson and Zaki for a monodensity monodisperse, but it clearly says that it is only applicable for n greater than 1. So, I cannot do it. Okay. So, but again I have got some doubt with this, but I will recommend that so far whatever model I have come across, let me admit here it is very difficult to guarantee that I have got access to all the literature, something maybe as a better model may be available in Polish language literature or maybe Chinese literature, I do not know. So, if you are really serious, you have to do that. I am not dealing with this right now, I am happy with these models, whatever I have got, okay, that can serve my purposes. So, the another limitation with this, still I can recommend that okay, Brouwer and Thiele's model are the best available model from the theoretical point of view, from the logical point of view, but nobody has validated it. that how good is match the predicted value, they match with my experimental values. Because again you can come out with some research problem, and if you can do it, I think yours will be one of the best PhD thesis globally. How do I measure? Suppose I have got 30% by volume of solids differing in size and density, and out of that I have to measure the settling velocity of one particular class of particle. How do I measure it? What type of measurement system I will be having? I invite the your instrumentation people, electronics people from different group. So, suppose if one student comes to me from instrumentation or electronics, I will give you the problem straight away. Tell me, how do I measure it? Okay. So, this is the problem with measurements even for this type of complicated systems. So, here what I did, again I compared it with some synthetic data, that is predicted velocities of quartz at low solids concentration, that is 6.89% by volume. Where from it has come? Because I wanted to do it in mass percentages, which we are more familiar with. So, when I am converting that mass into volume, it came out to be 6.89. Okay. And then the particle sizes, that is settling velocity, by using Brower and Lee's model and Richardson and Zaki. You see that all three models, they differ. There is no agreement. So, if someone claims that why you are not using Richardson and Zaki for this, you show this graph, that why you are saying, where is your measured data that I will use this. So, I cannot bias my mind with any of this model, rather I will go to the facts which can relate to my particular system. If it is monodensity, monosize, I will blindly use Richardson and Zaki, but for Mindered processing applications, rather I will use Brower and Thiele's model, because that logically it makes more sense. Okay. Look at that for a thickener point of view, that is what I was telling. When the concentration is high, you see that the Brower and Thiele is saying that some of these particles will have even zero settling velocity, that means they will not settle, and that is what we observe in many times in industrial settling chambers, that is your thickeners, and reason is here. This is the reason. Okay. But none of the other models, they give you a zero settling velocity, and that is why I fall in love with this Brower and Thiele model. Okay. That is another reason, because I can correlate it with my practical applications, and this is what we observe, isn't it? So, it does not matter how much of flocculant I add, the big particle will become bigger also. So, best thing is that segregate it into two different air and treat them into two different chambers, rather than putting more reagents into one chamber. From a fluid mechanics point of view, this type of problem may come, and the problem may be because of this. Okay. So, conclusions about hindered settling models, that is Richardson and Zaki model may be used for uniform density and monodisperse suspension. I hope you have understood what is meaning of monodensity and monodisperse. Okay. For polydense and polydisperse suspension, Brower and Thiele's model seems realistic. However, the model has to be validated well with reliable data set. I am not telling with confidence, but it appears to me. Okay. And I will first finally conclude, and this is what I wrote in a review paper also, this is published, that reliable hindered settling model is yet to be developed for practical use. Even though it has got vast engineering applications, we are researching it for so many years, so many good brains are working, but still because of the complexity associated with that, still it is not there. So, these are the fundamental areas where some of our Mindered processing and cold processing research groups should be working to develop basic models or to bring solutions, to design modifications to our processes. We have to do that, otherwise we cannot do that. Now, issues, if I summarize, inadequate measures of shape, size and orientation, as if I start with the characterization to this, that these are the research challenges I am posing it to you. Give me how do I measure shape, how do I define shape? There should not be any contradiction with that. Size, orientation, irregular shapes, sphericity, how do I know? For a multi-particle system, how do I know the sphericity of the different particle system? Viscoplastic, viscoelastic liquids very difficult to deal with. Wall effects, I do not know many times, how does it affect my settling under dynamic conditions like your dV by dt when it is not 0. Okay. Then hindered settling, we do not have models. Let me continue this for another half an hour, can we? Okay. So, now you have seen in that my introductory lectures, the first day on mineral processing and coal preparation, that we are using centrifugal force also. Now, these are all we have discussed only when we have used only a single G, that is your normal gravitational force field. Now, when I am rotating it, when I am introducing a centrifugal force, then what happens to the settling velocity of the particles? Okay. How do I calculate it? Now, I will make your life very simple, I will not deal with the detailed derivation of this. It is centrifugal force in radial direction if my system is moving is m omega square r, that is omega is basically 2 pi n. Gravitational force is Fg is equal to mg, and I can take a capital G, that is to denote the ratio between this Fc and Fg, that is omega square r by g. Okay. Now, if you look at, there is a book by Su, HSU, is also from University of Queensland, that is the theory of centrifugal sedimentation, or it is a theory of centrifugation, I forgot the name, but it is Su, HSU. Okay. It is a good book. There you get all the derivations for this, that is in a centrifugal force field the equation of motion takes the shape of this. And finally, for a very small particle, again I have to go for Stokes region, Newton's region, and your tangential region. The good thing, now you see that in his book he has now given a value of 0.2, okay, and the maximum limit is also 10 to the power minus 4. Below that, your say body forces are having no effect, they are basically the surface forces become active. So, van der Waals region you are going, so you cannot probably use this say physics. Okay. So, I have given that. So, B is denoted by that, that is your omega square term is coming, and if you look at the in terms of G, if you replace that, you can see that the centrifugal sedimentation velocity is G, that is the how many times of that normal gravitational force it is being used, multiplied by Vg, that is the settling velocity of that particle in a normal gravitational force component. So, if it is hindered settling velocity, it is Vth, if it is free settling velocity, it is Vt. So, I have written in a generic term at Vg. So, first thing is that I have to know what type of system it is, and I have to bring that and then multiply it with that. The interesting thing here, should I continue? So, interesting thing here that, so I can write V is equal to G Vg, but only when my particle Reynolds number is within the Stokes region. Now, in tangential region, when the Reynolds number is, now in that book it is written that your Newton's law is valid up to even up to 500, not 750. These are so many arguments and disagreements are coming in the literature, okay, saying that if Reynolds number is within 0.2 to 500, then it becomes square root of G into Vg. That is not directly you can write that it is the how much of the intensity of the centrifugal force. How do I explain it physically? Now, suppose I take a thread and I have got a very small particle at the end of that, and I rotate it and then I leave it, then the distance it covers, you see that if I take a particle of which is 1000 times more heavier than that, if I rotate it at the same RPM, if I leave it, will it reach 1000 times the distance it has covered, the particle? No, it will be less, because after a certain time the gravity forces will be more dominant to that, and that is the correction factor it is given here. Okay? That is, it has a function of your Reynolds number with the particle in a centrifugal force field. So, that is where what happens, it becomes square root of g multiplied by Vg, and if it is in Newton's region, it is cube root of g into Vg. The bigger the particle, the lesser the effect of centrifugal force beyond a certain range. That is, it has got effect, but not at that same level what it has got with the smaller particle. Okay? So, based on these equations, I have written one, there is a big problem with the hydrocyclone literature, it is called the Fisuk effect, and I showed it that it is not because of experimental error, not because of other condition, it is just a simple fluid mechanical behavior, abnormal, but that we will see that when we discuss about hydrocyclone, if we have time we can discuss that. Okay? That is one of my most frequently referred article. Now, we have discussed about all this, now we must be worrying that they are all boring things, what are the applications? Okay? I will give you some one or two examples, that is where I can use this knowledge in designing even, or in selecting the process conditions. Okay? So, automatic question will come, settling velocity, where are the applications in this course, because the course is on separation of fine and ultra fine particles using a fluid medium, and I said it is the basis. Now, so suppose I want to design a system to separate my coal and mineral particle. They have liberated both, and I want to have a basically a column like this, where I will feed at the central region the mixture of coal and mineral particle, and I want to have a rising water, so that my coal particle is basically carried towards the top and mineral particle can come down to the bottom. So, that my adjustment of my fluid velocity should be in between the settling velocity of these two particles. Okay? Now, you see that coal, the density I have given, it is 1.3 gram per centimeter cube, or you can say specific gravity is 1.3, and density, that is size of this particle is 0.6 centimeter, and mineral particle is density is 2.3 gram per centimeter cube, but size is 0.2. So, I do not know whose settling velocity is more and less. So, now what I can do, that is I can calculate it, I am talking about only free settling conditions. Now, you see what will happen. So, I have to calculate the settling velocity. First thing what I have to do to design this, I have to know that what will be the settling velocity of the particles. So, if I want to do an experiment for that, then it is gone, nobody will give me. So, I have to use the model, that is where I will be using those models. Okay? Which model? That is what we have discussed so far since morning. Okay? So, based on that, so the particles are in water, it could be air, anything, I can calculate it. Okay? Now, if I calculate the settling velocity, free settling velocities, the coal particle settling velocity is 23.6 centimeter per second using that iterative model, and Reynolds number is giving 1585. Reynolds number is not important here, but I am just for your curiosity I am giving, and mineral particle the velocity is 25.2 centimeter per second. So, that means first thing what I say, that it is possible to separate them. If they are both are 23.6, no way you can separate it by rising water. You can separate it, then I have to separate it based on only density effect. So, I have to have a medium density in between that. That is where your gravity concentration comes, but here I am talking about only the separation in a pure fluid. Okay. Now, you see, then now my water velocity, upward water velocity has to be monitored very closely in between these two regions, 23.6 to 25.2 centimeter per second. That is extremely difficult. That means my chances of misplaced particles in the other stream will be very high. So, that means my separation accuracy cannot be guaranteed. It is very difficult to design to have a precisely, say your suppose 24.5, if I take a mean value of that, become somewhat like that 48.8, so it is 24.4 or something. It is very difficult to maintain that 24.4. I have to have, because how I am having this upward velocity, it has to be pumped, there may be surges, there may be some operational problems. So, there is enough chance of say having disturbances. Now, here actually in free settling conditions, so I would say that it is very difficult to design, and at the same time I want to process large volume of material. So, it is good news, but then I would say that if I use hindered settling condition, what happens? That is the beauty of this modeling, if I know. Now, if I say that total solid concentration percentage by volume is 2%, mixture of that is 50-50 mixture, okay, then your velocity of coal becomes 21, it is reduced from 23.6 to 21 centimeter per second, okay, because of hindered condition I have used. Then minerals is 25.6 centimeter per second, that is some problem here. Why it is even that with mineral, there is some problem with this number, okay. So, there may be some typo, okay. So, it is marginally it should be 24.6 or something like that, okay. So, the 5 is basically typo. So, it should be 24.6 or something, and the pulp density is becoming 1019. That also I have to check, because if my slurry density is more than my density of my say the mineral particle, that is your coal particle is very high, it is approaching to this range, then my mineral particles will be having difficulty in settling. So, I have to look at that conditions also. So, and if I keep on increasing this concentration, you look at 30% by volume, my velocity of my coal becomes 2.35, and actually my intention was not to allow it to settle. It is better that my coal particle does not settle, so that it will be carried to the top. So, I want to reduce that, and you see how much is the drop in the velocity of my mineral, it becomes 15 centimeter per second. So, now I have got a range to play with 2.35 to 15 that can easily be designed, easily be monitored for upward velocity of my water, and at the same time I can process 30% of solids by concentration. But if I want to use a free settling, no, always we have got a notion in our mineral processing engineer's mind that lesser the concentration, better is the separation. Not always, not always, okay. And this is the classic example, and this is just calculation, okay. So, I have to do these calculations before selecting the right kind of concentration, okay. So, this is a classic example where you can use this knowledge in designing. Next one, that is what we discussed in the introductory one also. Now, I can know that the slurry is coming. So, if I know the settling velocity of my particles, then I know that this particle will settle here, and up to what distance it can be carried, if I know a little bit of fluid flow problem also that we have not discussed, then I know that what will be the dimension of this, what will be the width of this, based on my this range of the particles I wanted to have segregated. So, this dimension of this, mainly the width of this, I can design if I have a basic understanding of basic say flow problem, and the heart of this is the settling velocity problem. Okay. So, I can also design. It is not that simple that you just have these chambers and your particles will be collected in a separating condition, in a separated form. That is where the design means. And then if I say, suppose if I want to collect it in a continuous mode, so what we normally do? We put basically a valve here, and that valve is basically controlled by some kind of instrumentation that, and it senses that what is the load on that is your pressure gauge type of system and your solenoid valve, and then it says that the rate of accumulation, if accumulation is this much, so I will be having this much of pressure. then that solenoid valve automatically opens and then it drains out my particles. So, how do I do that? Only when I know what is the rate of accumulation of my particles, then only I can design, and my entire capacity of my system depends on that rate of your unloading this particle or say discharging these particles also. Otherwise, my gap between this and this will be marginal, then I will be having some misplacements, some particles which is supposed to come here, they will go there. So, how do I maintain this depth, uniform depth, because I have to collect that. So, these are, that is why that basic design thing you can get into, and the fundamental thing what I need to know, that is what is the settling velocity of the particles. Okay, that is how we can use it. Similar type of thing, that is your settling chamber also, I can design different types of settling chambers, which is dictated by the material characteristics as well as your need, that is the capacity and all this we need to have. So, this is the good thing about that, and even the thickener design, the basic information I need to have. There are many models in chemical engineering for thickener design and all this. I also teach them in my class, but I am not getting into that. But what I say that it does not settle vertically there in a thickener, it has got a settling velocity like this. Okay. But essentially you need to know this, that what is the settling velocity of this. So, here you see that if I am designing a thickener for fine coals, okay, so I know the density varies from 1.2 to 2.2, that is the beauty of my coal. So, I can easily calculate the settling velocity as a function of sizes, because I know they are minus 0.5. So, I know that what is the highest settling velocity particle and how much of them by size analysis I know, and if I am targeting that, and what is the lowest settling velocity particle I am having, I can easily design a thickener best depending upon my rate of your requirement of my solid liquid separation. Not arbitrarily choose a thickener that okay, I will have L by D like this, there must be some scientific basis, and these are the basic principles. So, if anyone is supplying you a design and if he has not collected your sample from your mine site, do not accept it, because this design is not tailor made to your material. He does not have any idea about your material and he is saying I have got a design. How can you design? Okay. So, this is what my intention was, that you may keep these presentations, you may enrich your literature with this, enrich your knowledge in this, but keep your mind open that how do I select. Do not go by the brand name of the organization or the person, you look at scientifically and look at that what should be my criteria. That is the very purpose of my talk. Okay. So, these are having huge industrial applications. Okay. Thank you very much for patient hearing.